be 2?
She gave it to me.
Wouldn't 2 always be the core electrons then? For one for charge?
No, not. This is just magnesium.
Yeah.
I could give you a larger element.
Okay, so but, why is it just 1s2 instead of 2s2, 2p6?
Why is this 1s2?
Why is 1s2 just the core electrons instead of 2?
Because now, let me show you real quickly. Because it was like this. It was 3s2.
Yes.
Right? But then, okay, this is a neutral magnesium. This is correct. For neutral magnesium, all of these are the core. You see this is the core.
Yes.
All the blue boxes, that's core. This is valence. Okay. So, our formula was 12 minus 10, and our overall Z effective was 2. We have 10 core electrons.
No, but that's the Z set.
Right?
Those aren't the free ones.
Now, what I'm doing is I'm taking 2 electrons away.
It's neutral. This is
That plus 2.
Yeah.
Taking 2 of these away. Oh my god! I took those outside away. So now, since that shell's been removed, there's no more electrons in the outside shell. Now, our outermost shell is this second shell.
Yeah, that's what I'm saying. It's because like.
So now we have just these 2 electrons as our core, and these 8 as our valence. So we only have 2 core electrons.
Someone's shaking the table. Someone keeps shaking the
Oh,
table.
it's me, sorry.
It's going to look like an earthquake on there. We've got 12 minus 2, so it's going to be plus 10 charge.
Okay.
Try it with other elements that are charged.
Yeah, I'll try.
Can
we do another
I
one?
suggest you try out some problems like potassium plus 1.
Okay.
Right? Try aluminum plus 3.
How will know for
Try,
You're asking tomorrow.
what else? I could just go down the line. I could do beryllium plus 2. Okay? Try these out at home and see how you do.
Do you have
You
a
can come in
practice?
and we can talk about it tomorrow.
Okay.
Do you have a practice site on
I don't have a practice site for this.
Yeah, that's it. Okay.
No, I'm just saying you can practice these 3. If you can do all 3 of these perfectly, and we can talk about them tomorrow, then you'll be fine. Okay? I believe you have the concept there. Okay? So that's when you have a plus 2 charge, or when you have a positive charge on an atom. If you have a negative charge on an atom, it's going to be the same, you're getting the same result as a neutral atom. Because I never give you a crazy, atom like this, like Br minus 2. That's just crazy. It will never happen.
Why is it crazy?
I'm just not going to give it to you.
35.
Okay?
Because why?
BR is 35.
Br is only, bromine is only going to gain 1 electron. It's never going to gain more than 1 electron. If it gains more than 1 electron, it'll just lose that electron instantaneously.
Can you do reactivity now?
Excuse me?
Can you do reactivity first? And then
Reactivity next? Is that, do you gotta go?
yeah.
Reactivity! Reactivity is pretty easy. Something's reactive if it can gain an electron easy or lose an electron easy.
Is it just, are you just going to ask for the definition?
No.
Oh, okay. I was like, yay.
No. So if something can gain an electron easy, then it's, and we found those trends before. This is kind of goes along with the trends.
Oh, nice.
Okay? On the periodic table, we can look at this. Okay? So it looks like it. As you're going across the periodic table, as you're going down the periodic table, you're going across, the atomic radius does what?
Decreases.
It decreases. Let's do Z effective too. Ooh, that's a nice one.
That increases.
That increases. Okay? What about Z effective as you go down?
The atomic radius decreases.
Oh, it decreases.
It decreases, but our formula doesn't say anything. This little formula, with this, which is ZF equals Z minus S, that is not affected. So the ZF does not get affected as you go down, but it does decrease as you go down.
It's the opposite of the atomic
It's just
radius.
that our formula does not help us know that. Okay? So the ZF does decrease as you go down, but
And the
our
atomic
formula
radius
does not help us.
increases as you go.
That's right. Atomic radius increases. So you can see that they're inversely proportional to each other. So they relate to each other, but in opposite ways. As one goes up, the other one goes down. As one goes down, the other one goes up. Okay? Now, what else we talked about here? Other trends are ionization energy. That's definitely important for reactivity. Because if you don't have much ionization energy, that means it's easy to rip off an electron. So
you don't have a lot?
Yeah. So if an atom's ionization energy is really low,
then it doesn't take much energy to get
a little nudge, and the electron will be kicked off. Okay?
Do you mean the other atoms, like
I'm talking about
ionization, or that atom?
that atom, if it has a low ionization energy. Okay? Low ionization energy means that just a little nudge will kick off that electron. Meaning that it's very reactive. So the elements that are very reactive are over here for ionization energy. They're losing their electrons because they have such a low ionization energy.
But I'm so confused.
So as you go across, ionization energy increases. And over here,
Yes.
as you go down, ionization energy decreases.
But I thought ionization energy, it applies to when you take it like from another atom. Like let's say beryllium wants to take it from fluorine. It would take a lot of energy to take from fluorine because it's more compact.
Bromine. You say fluorine?
You don't have
Fluorine.
You don't have to think of one taking from the other. It's just how, for example, like whenever the atomic radius is bigger, the more energy it takes, ionizing energy it takes to rip off an electron.
Yeah.
The bigger it is?
Yeah.
Why does that doesn't
Because
make
it's
sense?
easier, like it's like the iPod thing. If I have it here,
Yeah,
it's
it
here
takes
for
less
this
energy.
Oh yeah. Yeah.
Okay, yes.
The
Okay.
bigger the atom, the less energy.
The more compact it is,
Yeah.
the more energy. Yeah, okay.
I'm also writing in
So
electronegativity.
then you know that the bigger ones are the ones who have.
You can think
the
of
are
electro-
as well as the
Electronegativity.
smaller ones.
Like these and these.
Exactly. That's it.
So you can think of ionization energy and electronegativity as two peas in the same pod. Okay? Meaning that they're related to each other. Ionization energy is the energy it takes to rip away an electron from an atom. Electronegativity is an atom's ability to attract electrons. Okay? So you can think of those two as kind of the same idea. They're closely related because if an atom really attracts electrons, it's going to be really difficult to take any electrons away from it. Right? So as you go across the periodic table, it's going to be really hard to rip away electrons from any of these atoms. And these atoms are going to rip electrons away from other atoms. They're going to attract electrons to them. They have such a strong positive charge in the nucleus that they're going to be attracting their own electrons, and they're also going to be attracting passing by electrons. So both the ionization energy is going to go way up, and the electronegativity is going to go way up for these atoms over here on this right-hand side of the periodic table, especially up on top. Yeah.
Okay, so just to make sure I got it. So because the atomic radius is decreasing left to right, it's going to like become compactor almost, right?
Yes.
And that therefore the electronegativity is going to increase because the atom like is going to be more attracted. I mean, the electrons are going to be more attracted to the nucleus.
Yes.
And the ionization energy will increase because it's going to take more to take those electrons away from the nucleus.
That's right.
And the Zeph will increase because the Zeph is the charge felt by the valence electrons.
Right.
Okay, got it.
So if you want to think about this in terms of reactivity now,
Yeah.
right, which you all do, you think of these elements. I'm going to say the first two groups. I'm just going to cut it off there. These first two groups, I'm putting it in green. These green for give. They give away their electrons. Right? So they're really reactive. Over here, on this side of the periodic table, I'm just gonna say that these, I'm gonna give you guys just this group, the halogens, as being very reactive. Okay?
So the green is not reactive?
No,
Green is reactive, blue is reactive. It's just that here, these are giving away their electrons to make a reaction. Here, they're taking electrons.
But can you know this by looking at the periodic table and seeing a pattern or something like this?
Well, yes, they're valence electrons. Think about the valence
yeah.
electrons they have.
So valence electrons are increasing as you go this way, so you know that they're more reactive.
They're trying to become stable, and since the blue has 7 valence electrons, and to be stable you have to have 8.
Yeah.
It's only 1 they have to gain to become stable.
So the blue attracts more. Like it has a higher electric. Okay.
Yeah.
But wouldn't the group 1 be more reactive than group 2?
Yes.
Okay.
In the middle I put meh.
Yes.
They sort of react.